Hey, Alex. I was reading this article earlier, and it was talking about quantum computing, which always sounds super futuristic, right? But then it got into optical modulators and this challenge of scalability, and I was just kind of like, wait, what exactly is the big deal there? What's the hurdle?
Hadi, it's huge. I mean, seriously, it's been one of the biggest bottlenecks we've had in really scaling up quantum computers. For ages, these optical modulators, which are absolutely essential for precisely controlling the qubits with lasers, they were just, well, they were practically handcrafted, like artisanal instruments.
Handcrafted? Like literally someone building them by hand, one by one?
Exactly. Think about it, right? Every single qubit needs super precise laser control. And for that, you need a modulator. When you're dealing with a handful of qubits, okay, maybe you can do that. But once you start talking about thousands or even millions for fault-tolerant quantum computing, it becomes prohibitively expensive, structurally impractical, just not possible at all.
Wow. So it's like building a super intricate watch movement, but then you need like a million of them, and each one has to be perfect or the whole thing just breaks?
Yeah, that's a really good analogy, actually. And the inherent fragility of qubits means this precision is non-negotiable. So this artisanal approach, it really capped how big quantum computers could get. It was a massive engineering hurdle.
So what's changed then? How are they getting around this whole, handcrafted problem if they need so many?
Okay, so this is where it gets really exciting. Recent advancements, we're talking about microchip-sized optical modulators now. They're tiny, like nearly 100 times smaller than a human hair. And the key thing, Heidi, the absolute game changer, is they're using standard semiconductor manufacturing processes, like CMOS technology.
CMOS, that's like what they use for regular computer chips, right? So they're basically mass producing these things now instead of, individually crafting them?
Precisely. That's the whole point. Researchers, for example, at the University of Colorado Boulder, in collaboration with Sandia National Labs, they've actually developed an on-chip optical phase modulator using CMOS. It can handle high optical power, it's super efficient, and get this, it consumes significantly less voltage and microwave power than current modulators for quantum control. This means we can potentially produce thousands, even millions of these identical, reliable devices.
That's incredible. So less power, smaller size, and they're reliable because they're made just like any other mass-produced chip.
Exactly. It drastically cuts costs, speeds up development cycles, and allows for much denser integration. No more bespoke, expensive, fragile components. We're moving from a lab curiosity to an industrial scale component, which is just absolutely transformative for the field.
So if these tiny mass-producible modulators are becoming a reality, what does that mean for the bigger picture of quantum computing? What's next? What's the ultimate goal here?
Oh, the implications they're enormous. First off, the compact footprint allows you to integrate many modulators onto a single chip. This dramatically simplifies the control systems for things like trapped ion or trapped neutral atom quantum computers, which really need that individual qubit laser control.
Right, so instead of all these separate, delicate components, it's all on one tiny piece of silicon.
Yep, exactly. And this ties into the broader field of silicon photonics. We're talking about integrated photonics, where you manipulate light within tiny circuits on silicon chips. It offers scalability, compatibility with existing telecommunications infrastructure, and it allows you to put photon sources, processors, and detectors all on one single chip. It reduces noisy connections, improves reliability, and just makes the whole system much more stable and manageable than traditional bulk optic setups.
Wow, so it's not just making one part better, but actually making the whole entire system more robust and practical?
Absolutely. This is a critical step towards fault-tolerant quantum computing, which will eventually require thousands, potentially millions of precisely controlled elements. It's that shift from, can we even do this, to how do we build this at scale? This kind of systems engineering, Heidi, it's going to bring things like drug discovery, material science, and secure communication much closer to being a reality.